Okay, so in question 28, we're asked to figure out what the magnitude of the net gravitational force on the moon is. And it looks like we're going to assume that there are only two objects exerting a gravitational force on the moon, the sun and the earth. So let's draw those up. First of all, we've got the sun sitting over here. And then at some distance away from that, we've got the moon. And then at another distance away, that's obviously woefully out of scale, we have the Earth. So I'll label these objects up with their masses. So first of all, we've got the mass of the sun, which I'll call ms. And we've got the mass of the moon, which I'll call m. And we've got the mass of the Earth, which I'll call mq. No, actually, I think I'll call it me. That's probably better. All right, and between these objects, we have some distances, which, as I say, are obviously not to scale. So here they are. We've got the distance from the sun to the moon, which I'll call dsm. And we also know what the distance from the Earth to the moon is. So I'll call that dme. And pretty much, we're going to assume that these distances here are the distances between the centres of these objects, because obviously the distance from the moon to the sun is probably going to be a fair bit bigger than the radius of the sun, or obviously the moon. And similarly for the distance between the moon and the Earth. And that means that if we now know, which we do, the distances between the centre of these objects, then if we assume they're spheres, which they approximately are, then we can use Newton's universal law of gravitation to figure out the magnitude of the force that the sun exerts on the moon and the magnitude of the force that the Earth exerts on the moon. Now, which directions they're in? Well, clearly the sun is going to attract the moon, so the moon is going to experience a force out this way, which I'll call F ms. And the Earth is also going to be attracting the moon, so there's going to be another force vector acting directly towards the Earth, and let's call that F me. So we can use Newton's universal law of gravitation to figure out what are the magnitudes of these forces. So let's just go ahead and do that. So the force on the moon due to the sun and that's going to be what I've called FMS. And that, of course, is equal to the product of the masses of these two objects. Divided by the distance between them squared. So we're going to have dsm squared. And then the other thing we need to do is multiply that by Newton's universal gravitation constant, which is that big G thing, which we can look up in the textbook. So that's it pretty much. If we know numbers for each of these quantities, which we do, the question tells us numbers for each of these, we could just go ahead, plug those into our calculators, and then figure out what the magnitude of the force on the moon due to the sun is. And similarly, the force on the moon due to the Earth that's going to be given by an expression which is exactly the same, but with the mass of the Earth in place of the mass of the sun. And with the distance from the Earth to the moon in place of the distance from the sun to the moon. Now, so we have these two forces, and now what we want to do is to add those two forces up to get the total net force, sorry, the total force acting on the moon. So we have these two vectors here, whose magnitudes we can figure out from these two equations. Now, to add these two vectors, what we need to do is we take one vector, let's take FMS, stick it down somewhere. Then we take the vector that we want to add to it, in this case FME, and put it so that its back end is just at the tip of FMS, so the vector we want to add it to. So we have FME down here. And then the net force vector then is just going to go from the back end of the first vector to the tip of the second one. So the net force vector in this case is going to be pointing out this way. So this is our F net over here. And according to the diagram, the gravitational force that the sun exerts on the moon is perpendicular to the force that the Earth exerts on the moon. So we have a right angle round here, and so of course we have a right angle right there. So to figure out how long this is, well, given that we know how long this vector is and how long that vector is, or at least we could do if we plug numbers into these two equations, then we can use Pythagoras' theorem to figure out what the length of this hypotenuse is. So here we're going to have that the magnitude of the net force, that is the length of this vector here, is going to be just equal to the square root of the length of this vector plus the length of this vector. So that's by Pythagoras. And then, well, I suppose at this point we could plug numbers in and then get something for this and something for that and then plug those numbers into there. I don't really like doing that all that much because I find that when I plug numbers into my calculator, I tend to press the wrong buttons and I make all sorts of mistakes. So what I think I'll do is I'll just take these two expressions here and just plug them into this Pythagoras' theorem formula instead. So if I do that, then what I get is something like this. So I'm going to have a g squared and then multiplied by all this stuff squared. And then the same for this one. So again, I'm going to have a g squared multiplied by a me and m, and then divided by a dem squared. All squared. Now here what I see is that both of the terms under the square root sign have got this factor of g squared. So if we wanted to, we could factorize this out. And the other thing I see is that both terms have a factor of which is really just a factor of the mass of the moon squared. So if we really wanted to, we could factor out g squared, and we could factor out the mass of the moon squared. So this is just going to be equal to this. If we introduce a couple of sets, sorry, just a set of brackets. So we're going to have g squared times the mass of the moon squared. That's going to be equal to whatever's left over, which is just the mass of the sun divided by the distance from the sun to the moon squared, and then we still have to square all that, and then plus the mass of the earth divided by the distance from the earth to the moon squared, and then we have to square all that as well. And since we have g squared times the mass of the moon squared underneath a square root sign, it turns out that we can just pull these two factors out and make them sit outside the square root. So instead of squaring them and then having to take the square root immediately, we can just pull these outside of the square root, and we're left with something that looks a bit nicer. So we'll be left with this instead. So now we can go ahead and put some numbers in, but that's going to be fairly straightforward. We're given all those numbers, so we can just do that if we want to. So I reckon that putting those numbers into our calculators might be a little bit tedious. So what I've done here is I've just entered all the data that we need, just taken out the question and put it into this Mathematica document. And I'm just going to get Mathematica to do the calculation for me. So if I just enter in the equation that we just derived, it's going to be this. So the answer that we get after I make sure I shift enter here, so Mathematica knows what all the masses and the distances are, and also what Newton's gravitation constant is. So now if I just shift enter on the formula for the net force, I get that it's 1.37 times 10 to the 21. So if I go back to what I had before, I get that the number I obtained finally is about 1.37 times 10 to the 21 newtons, which is pretty big. But then so is the moon.